Hello class and welcome to this video lecture on atomic weights. Okay, so class, we have talked about different parts of the periodic table. We've talked about the groups, the periods, the symbols for the elements, the atomic numbers. What we have not yet talked about are the decimal numbers that you see but located below most of the element symbols. Okay, so we're going to talk about that. The decimal numbers that are shown below most of the symbols, those are called atomic weights. Okay, so let's talk about atomic weight. So the atomic weight, or we could call it the atomic mass, of an element is the weighted average of the masses of all isotopes of that element. Class, in your book, they're going to call it the atomic mass. It's also correct to call it the atomic weight. Now, weight and mass, are not the same thing, but I like to use this term atomic weight because it helps us remember that it's a weighted average of the masses of all isotopes of a particular element. Okay, it's not a simple average, but a weighted average. So I want to show you how we can calculate the atomic weight, how chemists do that. To calculate the atomic weight, one needs the masses of each isotope and the natural abundance or the percentage of each. Okay, so I'm going to show you an example. We're going to look at magnesium. Okay, magnesium. Now, magnesium has three isotopes. Okay, magnesium 24 has a mass of 23.9850 atomic mass units and a percentage of 78.70. Now, class, we're going to talk about where these numbers come from in just a little bit. Okay, so magnesium 24, this is the mass of that isotope, and that's the percentage. Magnesium 25, that isotope has this mass and this percentage. Okay, and magnesium 26 has this mass and this percentage. Again, we're going to talk about where these numbers come from very soon. These have to be measured, okay? So class, what this means is, remember how we talked about, with magnesium, okay? Magnesium, if we go back to the periodic table for just a moment, magnesium has 12 protons, right? A magnesium atom has 12 protons, 12 electrons. The neutron count can vary, right? The neutron count can vary. So some magnesium atoms have 12 neutrons, giving a mass number of 24. Some have 13 neutrons, some have 14 neutrons. So the neutron count can vary. What does that do? That makes the masses vary, right? So all magnesium atoms are not identical. They all have the same number of protons and electrons, but the neutron count can vary. So if I were to take a sample of magnesium and I analyzed that sample, what I would find is that 78.70% of that sample was magnesium 24. 10.13% of that sample was magnesium 25, and 11.17% of that sample is magnesium 26. That's what these percentages mean. Okay? Now, class, if I asked you, with these three, taking these three masses, what is the average mass? Okay, what you would do is what? For a simple average, you would add these up and divide by 3, wouldn't you? Okay, that's not what an atomic weight is. It's a weighted average, meaning we have to take into account these percentages. Okay, now the formula that we use for calculating the atomic weight, it's the same for every element. Okay, this is the formula. To calculate the atomic weight of an element, we take the percentage of the first isotope, divide it by 100, times the mass of that isotope, plus the percentage of the second isotope divided by 100 times the mass of that isotope, and we go on and on. We continue for however many isotopes the element has. Okay, so what I'd like to do, class, I'd like to work through this example with the data that we have. Okay, so I just shifted everything up a little bit to give us some more room. So what we're going to do, we're going to plug this information. We're going to plug in these masses and these percentages into this formula, okay, for magnesium. Okay, so we take the percentage of the first isotope divided by 100, right? Percent means, right, divided by 100, okay, times the mass, and I'm just leaving the atomic mass units off. This is atomic mass units. I'm leaving it off just to save a little bit of space here. Okay. We take the second percentage divided by 100 times the mass of that isotope, okay, plus the percentage of the third isotope divided by 100 times the mass of that isotope. Now keep in mind, class, again, we should have atomic mass units. The units are atomic mass units. I've left those off just to save a little bit of space on my slide here. Okay, now when we do the calculation, okay, keeping in mind, how many significant digits does this number have? It's got 4. How many does this have? It's got 6. 100 is an exact number, right? So when we do this multiplication and division, this should have 4 significant figures, okay? So let's go to the second one. We got 4 significant figures. We've got 6. So when we do this calculation here, we get 2.531 rounded to 4 significant digits. When we do this calculation here, okay, we get 2.902, okay? So we get these 3 numbers here, and then we add them together. Now remember, class, when you add, whichever term has the fewest decimal places, that's how many decimal places your answer is going to have. So we would end up with 24.31 atomic mass units. That is the atomic weight of magnesium. That is the atomic weight of magnesium, okay? So class, notice, this is not a whole number, right? If you look back on the periodic table, that's several slides back, let's do that. If we look back on the periodic table, okay, we see under magnesium, we see 24.31. 24.31, that we say is the atomic weight of magnesium. There is not a single magnesium atom that has this mass. These are the masses of the magnesium atoms, okay? But this is the weighted average. Why is it so close to 24? When you consider we've got 24, 25, 26, why is this so close, so much closer to 24 than all the others? Well, because that has the greatest percentage. The magnesium 24 isotope contributes the most to the atomic weight, right? This contribution was 18.88, 2.531, 2.902, okay? So we're going to say, when we talk about the quote-unquote average magnesium atom, this is the mass, or the atomic weight, we're going to say. Again, you could call this atomic mass, atomic weight, or atomic mass of the average magnesium atom, even though none of them have that mass, okay? All right, now, class, with this equation here, we've got 2 other options. Now, you know how to solve if you have one equation, one unknown, right? That's basic algebra. One equation, one unknown. Okay, so in the problem we just worked, we had all of the parameters we needed, and this was the unknown, right? We solved for that. But we could have a couple of other options. If we knew the atomic weight of an element, and let's say we knew the atomic weight and we knew the percentages. Let me show you here. Let me put them in blue. If If everything we know is in blue, if we knew the atomic weight, if we knew both of these percentages, if we knew one of the masses, we could calculate this mass, right? One equation, one unknown. You could solve for that unknown. Call it X, right? You could solve for that mathematically, okay? The other thing you want to keep in mind is this. Given the atomic weight and masses of isotopes, you could find a percentage. What do all of these percents add up to? What do they need to add up to? 100, right? All of these percentages to add up should add up to 100. So what I'm trying to say here in number 2, if you had only 2 isotopes, okay, the percent of A plus the percent of B should be 100, right? Okay, so I can make this one equation one unknown, okay? Let me show you what I mean. If I know the atomic weight, if I know the mass of both of the isotopes and I just have 2 isotopes, I could call this percent B and I could call this 100 minus percent B, right? Or I could call this X, right? And this would be 100 minus X because the percents have to add up to 100. What does this give me, class? This gives me one equation, one unknown, right? Remember, what I'm showing in blue here, those are all knowns. That's this scenario down here in number 2. So I can use this atomic weight equation to solve for different things, okay? That's what I'm trying to say here, okay? One equation, one unknown, that's what you need. Now, let's talk for just a moment about this. How do we know the percents? How do we know these? Well, as a student, you wouldn't necessarily know these. These are measured in the laboratory, right? These are all measured by instrumentation. An instrument called a mass spectrometer. A mass spectrometer is an instrument that gives you the masses of the isotopes and the percentages, okay? I want to just very, very briefly give you just a general overview of how a mass spectrometer works, okay? This is a very simplistic picture of a mass spectrometer, okay? So you've got some key parts. You've got the sample inlet. You've got some way of creating ions. You've got an electric field. You've got a magnetic field. You've got a detector, okay? So what you do is this. Let's take the example that we have here, magnesium. You have to get that sample into the instrument, and it has to be, as a gas, okay? This is very simplistic. You have to use a vacuum pump and pump all the air out of here. You have to have it evacuated, okay? And this sample inlet is really a very, very small opening, okay? But what you do, you have to heat the sample. You have to vaporize it, turn it into a gas, and then you have to ionize it. So class, you remember the makeup of an atom? You have the protons and the neutrons in the nucleus, and then somewhere outside the nucleus you have the electrons, right? Well, there are several ways that you can ionize a sample. One way is, through just hitting it with some energy. If you used an electron beam, you could basically, I'm putting it in very generic, basic terms here. You basically just shoot some electrons at the sample, at those atoms, and that knocks electrons away from the atom. So if you have an atom, a neutral atom, and you hit it with some energy and you knock some electrons away from that atom, that forms a positively charged ion called a cation, okay? So you form ions here, and then you have an electric field, okay? You can apply charges are applied to this plate, and that causes the ions to be accelerated, right? So if I have a positive charge here and I put a negative charge here, that's going to attract that ion. So through manipulating the electric field, basically, class, you could think of it as, you're shooting ions, you're accelerating ions through this instrument. Okay, so you've got a beam of cations coming through here, and those cations are magnesium ions. Some are 24, some are magnesium 25, some are magnesium 26. They all have different masses, and you're shooting them through here. Now, when they get to this magnet, that causes the beam to bend, okay, or the beam is deflected. Okay, it says here the magnetic field deflects the lightest ions the most. So you're shooting some ions through here. The ones that are the lightest are the ones that are going to be the easiest to deflect. So then you have a detector here. Okay, and the detector is going, every time an ion impinges upon the detector or hits the detector, okay, you can measure that. And so by measuring the total number of hits on the detector, and by measuring the number of hits of each isotope on the detector, you can very easily get these percentages. Okay. Now this picture, class, this is a picture from your book. This shows this separating into 1, 2, 3, 4, 5 beams. This is not magnesium. Okay. Magnesium would only have 3 beams, but I couldn't find a picture showing magnesium, okay? And I didn't want to try to draw it, so I took one from the book here. But this is actually showing a sample of zirconium, okay? So zirconium has 5 isotopes. Zirconium 90, 91, 92, 94, 96. All have the same number of protons. They have different numbers of neutrons, hence different masses, okay? So basically, you end up with a readout here that gives the relative abundance versus the mass to charge ratio. And that's how scientists get these percentages. So this is very straightforward, class, very routine in laboratories now. Now, mass spectrometers were not around in the early 1800s when John Dalton put forth his theory. Remember, in John Dalton's theory, he said what? All atoms of a given element are identical to each other. We know that's not true, right? Atoms, some elements have several isotopes, and the difference in those isotopes is what? The number of neutrons, and hence the mass. Okay? So class, I wanted to kind of give you just a general idea of this. You're not going to have to draw one of these, okay? You're not going to have to draw this on an exam or anything, but this just gives you an idea of how these numbers are obtained through this instrument. Now, we're going to see this instrument several times this semester. This is an extremely useful instrument for chemists to use, a mass spectrometer. So class, I hope that you have found this to be a helpful lecture on your understanding of atomic weights.